Alright, my name's Justin Hutches, and today I'm going to be talking about the mini cantilever lifting beam, which is also my senior design project. Some of y'all have probably seen some of these slides already, or similar, but going a little bit more background. The crane industry. Cranes are used to lift and transport heavy loads from one location to another. They're used in commercial construction such as power plants, building these towers, as you can see in this picture. I actually work for a crane company, Deep South, which I have on here. I actually designed some of the parts on this spar section and this outriggers. I guess I should explain that. This is the boom. The boom is used to actually lift these heavy loads. This is the mast. The mast keeps your angle between your cables from your boom to your spar, so it's not too sharp of an angle, so you can decrease that load on the cable itself. This is a spar section where your counterweights hang down and keep it level so it doesn't just crash. They're also used in public construction, such as putting bridges, roads, all that stuff, and many other industries. Different types of cranes. You have tower cranes, telescopic cranes, crawler cranes, pedestal cranes, truck cranes, which I'll get into later, but this here is a pedestal crane. What is a cantilever beam? A cantilever beam is a below-the-hook system used to lift loads in locations that aren't necessarily accessible by a normal overhead crane, such as like under obstruction, so they can reach in there and grab a load and pull it back out. There's multiple different designs of cantilever beams, and the most common is just a bar coming off the side of a building. Here we're going to be using a movable counterweight cantilever beam. The counterweight is able to move on a trolley back and forth on the system to keep the beam balanced whenever you're making a load. And this is a diagram we have drawn up for how it kind of works. You can see you have your truck crane system. The beam is under the hook on the boom section. Your counterweight is right here. It's moving back and forth, keeping the beam balanced, and we'll have angle sensors and everything on it to make sure it stays at the right angle. And you'll have two rigging points as shown with those two cables. The objective of this project is to design a beam that is smaller and does not weigh as much as what is already in place, so that's able to be used on cranes that are this size. And our budget is $5,000, even though we're designing a whole nother system than what we're prototyping, which has a budget of about $200,000. This is what's already in place. As you can see, they're clamping an extension beam on the end, which isn't very safe because it has to be changed each time they use it, and if it's not clamped correctly, it can just crash and drop the load from under it. The trolley system doesn't really operate as they would like to. They have to cut the chain every single time to use it, and it's just not very ideal for use. Some of the functions, it has to lift and transport loads for smaller truck cranes, operate in outdoor conditions, and it has to operate independently of the crane itself. So everything for this system has to be on the cantilever beam. So like if you put it on the ground completely off the crane, you can still use it. Constraints, qualitative constraints, it has to minimize weight, minimize cost, has to be weather resistant and easy to maintain. Easy to maintain is the most important because keeping up with the maintenance on these and changing batteries and charging them up and changing gears, any kind of parts is the most important thing in keeping these things and making them last long. Some quantitative constraints, it has to pick up 5,000 pounds of full extension, has to be less than 40 foot long. The trolley for the counterweights must move at least 600 millimeters per minute because speed is a big thing when you're out in the field. You don't want it moving too fast, but you don't want to be there all day either. And the angle of tilt for the beam itself has to be less than 5 degrees, so that's why we'll have sensors on there to make sure that that angle doesn't get too sharp and put too much stress on certain cables. So concept generation we started to do is trying to figure out how we're going to make the beam itself. If we're going to use just a normal I-beam, if we're going to weld two I-beams together, if we're going to make a box configuration with an extension, the trolley system, how we're going to move the counterweights back and forth on the beam itself, how we're going to supply power to the system, what kind of controls, if we're gonna use wireless or a wired control, radio signal, Bluetooth signal, how we're gonna get that done, where we're gonna rig it to, if we're gonna offset rigging points, inline rigging points, and if we're gonna use one or multiple lifting points for whenever we're actually picking up the load. And there's my references.